Well, good morning, Complex Gang. I hope you guys are staying healthy and finding plenty of supplies and perhaps even enjoying some of the downtime. Hopefully, you're able to keep up with your classes. I've heard a lot of students tell me that they're just getting buried with online classes. I guess these crazy professors think that they can just pile on more work, huh? It's true, actually. But yeah, I'm struggling to keep up as well, but excited that we're getting near the end here, just about 2 weeks left. So let me just give you a quick overview of where we're going as a class. We are almost done. We're going to look at some topics in Chapter 6, and then we're going to look briefly at applications in Chapter 7. So I'm thinking probably 3 homeworks left. It could be 4. We'll just see, but I'm thinking 3. I've mapped out where we're going, and I think I'll break it up into 3. So let's dive into this material. So recall, we saw this back in section 24. Let's do green today. We saw back in section 24 that we call a complex number z naught a singularity, or sometimes a singular point, whatever, of a function f if 2 things hold. So 1, f is not analytic at z naught, but then 2, f is analytic at some point in every neighborhood of z naught. And so the idea is, here's your z naught, and you're not analytic there, but if you draw a little bubble around z naught, I don't care how small you go, you can always find a little point inside that bubble where f is analytic at that point inside that little neighborhood. So just a quick example of this. Let's just do like the most basic example we can think of, 1 over z. So you can see that z naught equals 0 is a singularity of f. Why is it a singularity of f? Well, it's not analytic at 0, but in fact at any point non-zero, any non-zero complex number, so you can get arbitrary close to 0, any point around 0, this function is analytic. It's actually analytic everywhere except at 0. And so that brings us to a second definition. We want to be able to distinguish sort of levels of badness when it comes to singularities. So let's take a singularity, z naught. Z naught's a singularity of a function f, and let's call z naught, let me switch back to black, an isolated singularity of our function f, isolated singularity of f, if f is analytic on some deleted neighborhood of z naught. And so it's different now than the first definition. We're saying, look, you're not analytic at z naught. That's true because z naught's a singularity. So saying z naught's a singularity is telling you that actually you're not analytic at z naught, and then in every little neighborhood around z naught you can find at least one point where you are analytic. So isolated singularity is much stronger. It's saying you're not analytic at z naught, but there exists some little bubble. Maybe this one would be too big, but if you go small enough, you can find a little bubble around z naught where you're analytic on that deleted neighborhood. So it's the bubble subtract z naught itself. And so just 2 quick examples. So again, z naught equals 0 is an isolated singularity of 1 over z. You could see that. We already said that. Let's see something that is a singular point but not an isolated singularity. So 0 is a singular point of the principal branch log z, but it's not an isolated singularity because when you draw a little epsilon bubble around 0, you're not analytic at any of these points. So I don't care how small you draw it, you're not going to be analytic on the negative x-axis. So certainly not every singularity is an isolated singularity. For us, though, there's a key fact that really is going to be very important to know, and it's going to make life a little easier for us. So let's just suppose that you're analytic inside a simple closed curve C. And I really want to say inside, and I should add here, and on a simple closed curve C, except for a finite number of singularities. And I'm not going to tell you that these are isolated singularities a priori. I'm just saying there's a finite number of singularities. Well, it turns out that if there's only a finite number of them inside this closed curve, then you actually know each of them is an isolated singularity. So that's going to be important for us to realize, is that if you have a finite number of singularities inside a simple closed curve, then each one of them is actually an isolated singularity. And just to be clear, here's my closed curve C. I'm imagining these are my singularities. So first off, they're isolated, meaning that there's a bubble around them on which f is analytic on that bubble except at the point z0. But also, you can draw a little bubble around each one of these and keep them inside, keep the whole bubble inside C. So I want to make it clear, these Z1 through Zn, these live inside, not on C. So f is analytic on C and then inside C except at these points. You know that these are isolated singularities, and you actually know that you can draw a little teeny neighborhood around those points where the neighborhood itself is entirely contained in C. All right, so let's stop this video here, and then in the next video we're going to